Okay, hello everyone. Welcome to today's lecture, and please confirm that you can hear me clearly and you can see my screen. Okay, thank you. Thank you. Okay, so remember what we were doing last time? Last time we were saying, okay, how we can design the memory address decoder such that a given memory chip becomes enabled or it is selected only for its desired address range, right? Which basically mean that if the address is destined for that particular memory chip, we want it only to become enabled at that time point. Otherwise, we want it to stay disabled, right? And we said that to build such a memory address decoder, we need to know how the logic gates work. So we had covered the discussion about AND gate and the OR gate, right? We will start from exactly the same point where we left. So is there any question before I start today's lecture? Is there any question regarding previous lecture? No, okay. Okay, so remember last time we discussed and OR gate. Today we are going to cover, or we are going to first start talking about the NOT gate. So NOT gate is actually, it implements the NOT operation as clear from its name. So which basically mean that whatever is the input, the output is reverse form of that. So which means like if the input is uh, so if the input is 0, the output will be 1. And if it input is 1, the output will be 0, right? So it simply complements or simply reverses the output input, okay? The lab is open today, right? I want to show to the TA my work for the lab. Uh, yeah, I expect, okay, can you please hold this question for like for last 5 minutes? Then I will take care of it, right? Right now, I want to focus on the lecture. The lab related question, I can answer them at the end of the lecture. Okay. Please remind me. Okay. So the next gate is NAND operation. So NAND operation is basically not and. So it is equal to not and, which basically mean that what you do is that if you have two inputs, on those two inputs, you first perform the AND operation, and whatever result of AND operation is, on top of that, you perform the NOT operations, which mean you simply flip the output. Okay. So just to like make it clear for you, let's say I am putting here A, B to indicate the AND operation, right? So from our previous knowledge, we know that if the both inputs are, if any of the input is 0, the output is 0 for an AND gate, right? So here the output will be 0, this will be 0, this will be 0, and here the output will be 1, right? But this is AND. Now to make it NAND, what you do NOT operation on the output of AND. So when you do NOT operation, so all these zeros, they will become 1, and the 1, it will become 0. Okay. So this is the truth table of the in 2-bit or two input NAND gate. And again, this is the symbol to represent that NAND operation is performed between two inputs A and B, and this symbol AB and then a bar on top of that, it's mean NAND. Okay, so AB means AND operation, and but if you write AB and a bar on top of that, it's mean a NAND operation. Similarly, in the previous slide, this was the symbol of the NOT operation. Okay, if you have any question at any point, stop me. Okay. Okay, so the next gate is exclusive OR. So again, here we are going to focus only on 2-bit exclusive OR. Again, it is possible that you can do the exclusive OR between 3 bits or 4 bits, or AND operation between 3 or 4 bits or more than that. And same is true for OR, NAND, right? But we are keeping our things simple because we are focusing only on two input gates, right? So here again, we have two inputs A and B, and we do the exclusive OR operation. So the result of the exclusive OR operation, or the exclusive OR operation between A and B, is indicated by this symbol. You have a plus sign enclosed in a circle. Okay. And how it works, like, so the output of an exclusive OR gate is 1 only if only and only if one of the input is 1. If both inputs are 0 or both inputs are 1, then your output is 0. Okay, so It is different from OR. Remember what was the operation of OR operation? As long as any single input is 1, the output will be 1. However, in exclusive OR, your output is 1 only if at most one input is 1. Okay. So here the output will be 0 because both inputs are 0. Here the output will be 0. Why? Because both inputs are 1. Right? But in these two middle cases, output is 1 because only one input is 1. Right? Here B is 1 and here A is 1. Okay. Okay, now we are done with our discussion of the basic logic gates like AND, OR, NAND, exclusive OR, and NOT, right? We haven't covered NOR, but it's not important. Okay, now we get back to our question that we want to design a logic circuit of basically a memory address decoder such that the memory with which we connect that address decoder, that memory becomes enable, it is selected, so which basically mean here we get 0 only for the given address range. So for example, we want this logic circuit to enable our this memory chip only if address is in the range of 0 and 15. Why? Because it has only 0 to 15 location. In total 15 locations, and they are addressed. Those locations are addressed starting from 0 to 15. Okay. So if the address placed by the CPU on this address bus is within the range of 0 to 15, we want this circuit to memory to become enable, which means we want this logic circuit to produce a value of 0. And if the address is greater than 15, let's say 16 or 17 or anything greater than 15, then we want this logic circuit to produce 1, which means that this memory will be disabled. Okay, this one will be disabled in that case. So now how can we design that logic circuit? Remember, we said that we can design using the gates, and now we have the knowledge of gates. So for that, what we do is that we write the address range in binary. What address range? Given address range. For example, in our case, it is our desired address range is 0 to 15. So we want this memory chip to enable whenever the address placed by the CPU on the bus is within this range, right? So we first step is to write the address range in binary form, right? So smallest address is 0. So we are creating an 8-bit binary of the address, right? And the largest address is 15. So we also write the 8-bit binary of the largest address. So in the range, right? In the desired range, 0 and 15. Then the next step is that you separate the fixed part of the address, right? You look at the bits which remain fixed, which do not change between the minimum value, minimum address, and the maximum address, which is basically these 4 bits, higher 4 bits A4 to A7. They stay 0. The other bits like A0, A1, A2, and A3, they can change depending upon the address value within the range. For example, let's say if the address is 7, what will be the value of the address? 8-bit value of 8-bit binary of the 7. Address 7 will be this one. So you see again that these bits stay same as in the minimum and the maximum, but these bits are changing. Like for example, let's say if I say the address is not 7, let's say I consider 10. So for binary 10, for 10, what is the binary? 0, 0, 0, 0, 1, 0, 1, 0. Again, you see that these 4 bits are same, they are fixed, but lower 4 bits they are changing. Okay, so in the second step, we separate the fixed part of the address. And then the third part is that we use a NAND gate to design a logic circuit whose output activates when the fixed address is given to it. So basically now we will simply use a NAND gate such that the output of the NAND gate will be 0 only uh, when the address is in this range, like 0 to 15. As soon as the address becomes greater than 15, its output will become 1. Okay, so let me discard these annotations so that you guys can see the slide clearly. So what we do here is that all the we use only those bits from the address which have the fixed values in the whole range, right? Which mean A4 to A7. So we are using only A4 to A7, right? And in the fixed version, if those bits always have the value of 0, we simply put a bubble, which mean complementing, right? Taking a knot. So we are first taking a knot of A4, right? And knot of A5 and knot of A6 and knot of A7 and then feeding it to the and NAND gate, right? Remember, this is NAND gate, right? But these bubbles at the input, they are indicating that we are complementing or we are flipping the input. But we flip the input only if the value of these bits is 0 in the fixed part of the address. Since all of them are 0, so we are putting bubble on all of them, right? So this will be our memory address decoder. Now let's test it, right? So let's test it by having an address 12, right? Let me generate 4-bit binary of 12, right? So 8-bit binary of 12. So 8-bit binary of 12 will be 0, 0, 0, 0, 1, 1, 0, 0, right? So this is A4. It's difficult to write here, but bear with me. This is A4 and this is A7. So you are feeding these 4 bits into the input of the NAND gate, right? So what will happen? A4 complement. So here you will have 1, 1, 1, 1, 1, right? After the complement, all of them will become 1. So when all of the 4 inputs are 1, what is the output of AND gate? It will be 1. But remember, on the output will again have a bubble, which means complement. So it will become 0, right? So our chip will be selected. Why? Because our address was in the range, within the range 12, right? Now let's select an address which is not in the range. For example, let's select 16. Okay. So what is 8-bit binary of 16? 0, 0, 0, 1, 0, 0, 0, and 0. So we are feeding most significant 4 bits to the NAND gate, right? So A4, let me use a different color because so A4 is now 1. So when you take the complement due to bubble, so it will become 0, right? And all other threes are 0. So when you take their complement, you will get 1, 1, 1. Now when you do NAND between 4 inputs and one of them is 0, the output of that NAND gate will be AND gate will be 0, right? But then we also have a bubble on the output. So you need to flip it. So when you flip it, it will become 1, right? So which means that chip select is getting the value of 1, which means that this memory chip will be not selected or not enabled. Is everyone clear on this? If you have any question, ask me. Yes, thank you. Thank you for confirming. Okay. Now, here is an example. Let's do this together and then I will give you an exercise, okay? So design an address decoder for address from 300 hexa to 3FF hexa, okay? So it is an hexa form, H mean hexa form, right? So 300 is the lowest address in the range and 3FF is the highest address in the range, right? So what is the first step? Write the address range like minimum value and the maximum value in the binary form, right? So when you write what is the binary of 300 hexa? You remember how we convert? We replace every digit in the hexa form with 4 digits in the 4 bits in the binary, right? So this is the 4-bit binary of 0 in hexa. This is 4-bit binary of 0 in hex form. And this is 4-bit binary of 3 in the hex form, right? And then we also do the same thing for the maximum address, right? So the 4-bit binary of F is 4 ones. 4-bit binary of F is again 4 ones. And this is the 4-bit binary of 3, right? Now we look at the address part which stays same, right? So we separate that part. So this is the part which is now you can see in the block. And now we will use only these bits which remain fixed in constructing the decoder, right? How? We will design the logic circuit. So remember we said that those bits which have in the like fixed part of the address, those bits which have value of 0, we will first flip them by putting a bubble and then feed them to the NAND gate, right? So A8 and A9, they have value of 1, right? So we don't put a bubble on them. We don't flip them. Then is 10 and A11, they both have value of 0. So we are putting a bubble on these two inputs. We are flipping them and then feeding them to the NAND gate, right? So this is how our address decoder will look like. Again, after the lecture, maybe you can do the exercise just like I did in the previous slide to validate the address decoder by feeding it any address within the range and then feed it an address which is out of the range. So for addresses which are within the range, the decoder should give you a value of 0. And for those which are out of the range, it should give you a value of 1. Okay. Is it clear? So there is an easy way of designing. So what you can do is simply put a NAND gate for those bits across those bits which stay fixed, and then all those bits which have 0, simply move them. So replace zeros with bubbles and keep 1 as it is. Okay. So this is like an easy way to remember. Okay. Okay, now let's do this exercise and you have 2 minutes. Actually, let's have 1 minute. Okay. So design an address decoder for the range 0x50 to 0x5f. So let me know when you are done. Done. Good job. Let's wait for some other people also to complete. Thank you. Thank you for letting me know. I'm noticing that almost same set of 5, 6, or 7 students they are responding while other students are not responding to the questions. Uh, I will highly encourage you to do these exercises. Another way is like I should design the polls and then enable those polls during the during the lecture, and then I will be able to see that what percentage of the audience or participants have responded to a question. But then it will slow down our speed at which we are covering the course. Why? Because it takes time to and launch the poll and then close it, and so I don't want to waste time, right? So please do on your notebooks and respond. Even like if you are not able to like complete it and you think you need more time, let me know. I will give you more time. Okay. But you need to tell me. Okay. Thank you for informing me. Okay. So here is the solution. So you are simply first writing the binary, right? You can actually write 8-bit binary if you want, but just by putting a 0 here, extra 0, right? And then you are, how to say, you are taking the common digits or the fixed part of the address and then simply replacing it with the NAND gate. So if you use the 8-bit bits, then you will have an extra line here and it's fine. Okay. Okay, now another example. Design a decoder for memory address from 0xC0 to 0xF4. You have 1 minute. You can use 8-bit binary when you are translating the addresses to binary form. Thank you. Nice. Good, good. Good. Thank you. Thank you, everyone. So let me do it quickly here, right? So 0xC0. When I write its 4-bit, 8-bit binary, it will be 1, 1, 0, 0, and then 4 zeros, right? And when I write the binary of F4, I'm not writing 0x. It's definitely hexadecimal. So it will be 1, 1, 1, 1, and 4 will be 0, 1, 0, 0. Now we need to keep which part? The part of the address which is fixed in the both cases, which is this one, right? So I simply design, uh, I simply use a NAND gate with two inputs, and this is A6 and this is A7, address 6 and address 7, and this is chip select low. Okay. Thank you. Thank you for letting me know. Okay, let's continue then. So we are done with that part, how to design the memory address decoder, right? Now let's have a look inside the CPU itself, right? So CPU, it contains different components. Again, this is a very simplified version of CPU. Otherwise, if you like, because this is not a course on the architecture, so that's why we are keeping it very simple. Otherwise, if you take an architecture course and you look inside the CPU, it's super complex, okay? But here we are keeping it very simple. So one thing inside the CPU you have is program counter. The job of the program counter is to hold the address of the memory from where the next instruction will be fetched and executed, right? Remember, we said that I don't know whether I mentioned it in this course or the other course which I'm conducting this time in this semester. So your program is loaded in the program memory. And what is a program? It is a sequence of instructions, right? So when you execute when we say that a program is executed, actually what happens? The CPU executes these instructions in sequence one by one. Again, we are keeping things simple, right? Like we are assuming there are no branches in our program, there are no loops, like it is simple sequence of instruction, right? So how do CPU know that which instruction is to be fetched next? The instruction that is to be fetched next, where is it located in memory? So in memory, there is an address for every instruction. Like let's say I'm starting from 0, 1, and so on. You would continue like, I don't know, up to n, right? So the PC, it holds the address, program counter, address of the next instruction in the which like where in memory the next instruction is located. And using that, and like for example, if PC says 10, so it's mean that the next instruction that will be executed is the instruction located in memory at address 10. Okay. Instruction decoder. The job of the instruction decoder is basically uh, to try to understand the instruction which is now fetched in or read from the memory. What is this instruction trying to do? Like, what is this instruction trying to accomplish? For example, is it an add instruction, or is it an like AND instruction, or an instruction which wants to do the AND operation or OR operation or add or subtract, right? And not only that, the job of the decoder is also to understand that what operands are operated on by this instruction. Like for example, if it is the add operation, the instruction is saying do add, but add what? Like add the numbers, where are those numbers which this operation is instruction is asking to add together, right? So the job of the instruction decoder is to find that information. Okay, where are those operands, or where are those numbers, from where to get those numbers, right? And then ALU, arithmetic logic unit. So the purpose of this unit is basically to perform the operation. Remember, the job of the instruction decoder is to understand what operation is to be performed and where are the operands on which operation will be performed. The job of the arithmetic logic unit is to actually perform the operation. So for example, if the instruction decoder finds that, okay, the instruction needs to do the addition, and then ALU will actually add the numbers. And registers. So registers are actually how to say, the data holder. So for example, if the instruction was add, and then instruction decoder decodes it and finds that it is add, then it will also find where is the data, is it in which registers. Like here we have kept it very simple by naming the registers A, B, C, and D, right? So the data will be then, for example, if it was add, and our decoder found that, okay, the data is in register A and register C, then the data will be fed from A and C into ALU, right? And then ALU will do the add operation, right? And let's say if instruction also tells to write the data back in register D, so it will be written back into the register D. Okay. If you have any question, please ask. Okay, here is an animation which will actually help you to understand how the internal components of the CPU are used during the execution of a program, right? So let's first have a look at the program itself, right? Uh, Let me save it here. Okay. So here we have this program, right? So, but this program is not even is written in assembly. It is just written in some form of pseudocode. So basically here what we are saying in the first instruction is saying that read the data from address 17, right? And put it in register A. Then put the value of register A in B. Then read the value from address 6 and put it in A. Then read the value, add the value in register values of A and B together and put the result back in A. And here it is saying write the value of register A into the address 7. Okay. But this is again just a pseudocode. Later on, we will see how to do it in assembly language, right? But the important point is that all the instructions, whether you write them in assembly, even when you write in assembly, they are actually basically converted into the into bits, right? Like 1, 0, something. It converted into a code, a binary code, right? But for our ease of understanding, we don't represent that code in binary form, but in hexadecimal form by combining every 4 bit of the code and then representing them as a hex character. So for example, the code of this first instruction is 31 hex, right? The code of the second instruction is C4 hex. Code of the next instruction is 26 hex, and so on. Okay. So we have like how many instructions? 5. And we have here like more than 5 is codes, but they actually mean the point is like for every instruction you will have a code. Okay. Now everyone is clear on this part of the figure, right? Like you have a CPU and everyone now knows that what is job of each component and what is the job of the PC, what is job of ALU, what is job of instruction decoder, and what is job of registers, right? The other than that, we have these IO devices, right? And when we say IO devices 16, so it's mean that this IO device is connected at address 16. This is connected at address 17, address 18, and at address 9. And okay. Here we have logic circuit, right? Uh, and our code, basically, this code resides in memory, right? Okay. So now let's start our animation, okay? So Okay, let me go back. First, see here that PC is equal to 0, right? So if PC is equal to 0, it's mean that the first instruction that will be executed is 1, which is located at address 0. So first column is basically shows the address, and second column shows the uh, the code of the instruction stored at that address, right? So when we start, so address 0 is placed on the address bus by the CPU. Whatever is in the PC, CPU places that address on the address bus. And then since it wants to read the instruction, so it enables the read signal telling that, okay, I want to read from this address 0, right? So now our logic circuit definitely will enable the chip, and the instruction code from the address 0 will be read, and it will be brought into the instruction decoder here. Okay, so now instruction decoder will decode it, and then after decoding it will understand, okay, I need to read the value from address 17 and put it in register A, right? So it's mean that it need to read again from the address 17. So what it will do, that now this read is gone here. So PC is incremented. Remember, after every instruction, you increment the PC. But before you place 1 on the address bus, you first put the 17. Why? Because the instruction which you decoded, it says read the data from address 17. So PC places 17, and then it enables this read signal again. Now, who is connected to address 17? This IO device, right? So it will provide the data. Let's say the data it provides is 9. Okay. So that data is fetched, is placed on the data bus, right? And then what does this instruction say? Put it in A. So this will be moved into the register A. Okay. If you have a question at any point, you can stop me, because we are running an animation and it is a bit long animation. It will be difficult for me to start again if you have the questions at the end of the animation. So during the animation, if you have a question at any point, please stop me. Okay. Uh, okay. So next thing is, now the value of PC is placed on the address bus again, which means that now the next instruction, which is this one, will be fetched, right? So again, the read signal is enabled so that we can read the instruction. The instruction is brought it in and it is then decoded by the instruction decoder, right? So instruction decoder, by the way, so PC is then incremented to 2. Okay, when instruction decoder now decodes that previous instruction, it finds that it says move A to B, right? So what is the value of A? 9. So this will also move to B. Now A and B will have the same value. Not move, best with the, I think to say copy is a more right or appropriate word. Okay. After that, the next value of the PC is placed on the address bus again, and again the read signal is enabled, is like made active. So then the value instruction from the next memory address, which is 26, is read into the is fetched, and it is decoded by the instruction decoder. Now, what is this next instruction? It says read the data from address 6 and put it in A, right? So first thing, that PC will be incremented to point what is the next instruction to be fetched. But before placing the PC on the address bus, CPU will first put the address 6. Why? Because when you decoded the previous instruction, it says read from the address 6. Okay. So as 6 is placed, and then read signal is again enabled, right? So now what is the value at address 6 here? It is 5H. So this value will be read next. It is placed on the address bus, and then what did the instruction say? Put it in A. So it will be moved to register A, right? Now we are done with this instruction. So now CPU will place the address 3 on the address bus, and it will drive the read signal, enable the instruction from the address 3, which is 81 hex, is brought in and decoded. And when you decode it, it tells you add A and B and put the result back in A, right? So 5 plus 9 will be, so PC is incremented definitely. and then your 5 and 9, they are added together, which means both values are supplied to the ALU. ALU performs the addition and writes the result back in the register A. Okay. After that, PC is placed on the address bus. Read signal is made enable or is activated, and the next instruction from the address 4 is brought in or decoded, right? So when you decode, it says put the value of A in the memory address 7. Where is the memory address 7? This one, right? So what it will do is that it will write the memory, right? So first it increments the PC and then puts the address which is 7 on the address bus and the data which is A, value of A. So it is E. So E is placed on the address bus, and this time the signal is enabled, right? Because now we are writing the memory. So depending upon the address, the logic circuit will enable the memory. Write signal is enabled. So now what will happen, that this will be value EH will be written into the address 7 of the memory. Okay. So this is how like your execution of a program uh, is performed by your CPU at a very high level. We have like skipped very many details. We don't need to worry about them at this point because this is not a course on computer architecture, okay, or operating systems. Any questions? Okay. Okay, so we have seen in the previous slide, we have seen instructions, right? So an instruction is basically divided into two components, which is opcode and operand. What is the job of opcode? Opcode tells that what operation is to be performed, right? For example, do you want to need add operation? Do you want to simply do move or copy, just like we did in previous examples? Some instructions were simply copying the data from one register to the other or from register to memory, right? So what opcode tells you what to do, what operation to do, like right? And operand part of the instruction. So actually, operand part of the instruction, it tells you that where to read the data on which you are required to perform the operation, right? So when I say instruction, it's mean the instruction code. Like for example, in previous example, we were having instruction code of let's say 31 hex, right? So if I can, then it is converted into binary form. What is the size of the binary? It like depends upon your chip. Like in micro at Mega 328P microcontroller, it is it will be different, like 8-bit. 8-bit? No, it is different, like 16-bit. Okay. But in other processors or other microcontroller, the number of the bits, the size of the bit pattern can be different. It is not something which is fixed across all the platforms. Okay, so but the basic idea is that instruction code is divided into two main components. There can be other, but two main are very common, right? Opcode and operand. So here is an example. And by the way, here we are showing that all the opcodes are on one side and all the operand code bits are on the other side. That is not completely true. In some architectures, that is the case. Like opcode is all the bits which make the opcode, they are grouped together at like one physically at on one side, and all the bits which represent the operands, they are grouped together physically on the other side. But that is not case in the ATmega 328. For example, if you look at the opcode of the add instruction, right? So the opcode is distributed. So here these bits, these 6 bits, they make the opcode. Actually, it's not distributed here, but in some other code of some other instructions, the bits which make the opcode, they can be like distributed. Like maybe you have 2 bits here and then 2 bits here and then 2 bits here, and together they make the opcode. But in the instruction in the opcode in the sorry the code of the add instruction, they are not distributed. So here the first 6 bits from the higher significant side, they represent the opcode for add, and this opcode will always be fixed. Actually, what happens that, remember we said instruction decoder, it's the job of the instruction decoder to find out which operation is to be performed, and how it finds. it checks the opcode. If the opcode is zeros, four zeros and one one, it means that add operation is required. Okay. If let's say it is 00010, then some other operation. So which means basically that opcode for add will always be fixed. Okay. And now the operand bits, they are the remaining bits are used as operand bit. And here in add instruction takes two operands. Like two, it wants to add two registers. Let's say A and B. Like if we follow the example from the previous slide, A and B. So these RD bits, these are known as like destination register, and this is like source register, right? So if I said add, I don't want to write add because it take time. I'm simply writing add A and B. So what I'm saying is, what I want is this: add the content of A and B and put the result back in A. So that's why we name A as the destination register and B as the source register. Although both A and B are the source registers, but A also serves as the destination. Now, these bits, like bit 0 to bit 3 and bit 9, these together are used to specify the source register, and bit 4 to bit 8, they are used to specify the destination register. You don't need to memorize it. No, I'm just telling you that this is how an binary code or the code of an instruction looks like. And the template can vary from one instruction to the other. For add, it looks like this one. Okay. And you don't need to memorize again. Okay. So remember we said that opcode tells us what to do. And actually it tells that opcode is the tool through which instruction decoder finds out what operation is requested, right? So if, for example, if opcode is 3-bit 0, we are just making up an example. Let's say we have we use only 3 bits to code the opcode, to encode the opcode, right? So if all zeros, we can say we are reserving it for move operation, move the value, immediate value X into A, move a number into A, register A. 001, it's mean, let's say, move data from some memory address X into A, right? Into register A. 010, we can say that, okay, we are reserving it for the operation, which means subtract the value of A, subtract the value of some register X from A and write the result back in register A, right? And 011. So this is not, these are not the exact opcode used by ATmega 328P. We are just giving you an example. Like, for example, if you are building your own microcontroller, and in that microcontroller you have to design an instruction decoder, and you need to use the opcode. So this is one possible encoding 3-bit, and you say, okay, I will always have 3-bit opcode. So you can support 8 different operations, right? By reserving 1-bit pattern for one particular operation. Okay. So now, yeah, remember this is the same thing, same program example from the previous slide. So what happens, for example, if you have the instruction which is saying read the data from memory address 17 and put it in the register A. So depending, then it will be converted into the code, like for example, 31 hex. So because uh, this form is for our human readability, right? 31 hex is again for our readability, but actually it will be translated into a binary code. How it will be stored in the hardware, it will be in form of bits. So the 3-bit code of the binary form of 3 is 0011, and binary form of 1 is 0001. Okay, so this is actually your binary code of the instruction. This is hex code of the instructions, and this is the pseudocode. Okay, I wrote S. Actually, it should be P because pseudo starts with P. So branch binary code, hex code, and the pseudocode of your program. Okay. So this is what is actually stored in your hardware, or this is what your digital hardware understands. These are for our own readability. So the level of readability increases as you move on this side, right? So binary code is most difficult to read and understand. Hex code is relatively, you can quickly read it, but then doesn't conveys any meaning. But the pseudocode, it is easy to read and it also conveys you, it is also meaningful. Okay. Uh, remember, I guess in first lecture we talked about like features of the ATmega 328P. Like we quickly talked about, we said it is a RISC architecture, it is a Harvard architecture, and then at that time I said I will explain what is the Harvard architecture and what is like opposite of it, or what is like yeah. So, however, so one thing is there are two main types of architecture in terms of like how they access the memory. One is von Neumann or Princeton architecture. So here the main feature is that you have different different memory to hold code and different memory chip to hold data, but both of them are connected to the CPU using the same data bus, address bus, and control bus, right? Which means like if CPU want to read an instruction, so it will be then using this address bus and that and the data bus and the control bus to read the code memory, right? Code to read the code from the memory, which means that when it is reading the instruction, it cannot read data from the memory data memory, right? Because why? Because the buses are occupied for reading the code memory, right? Which means that uh, the two operations need to wait for each other as they cannot be performed simultaneously. So this design is simple in the sense because we are using the same data bus, address bus, and control bus to communicate with both code memory and data memory, but it is slow, right? And compared to Princeton architecture, we have Harvard architecture, where you have a CPU, you have a separate code memory and data memory. The difference is that you have separate set of data bus, address bus, and control bus to connect, to communicate with data memory and the code memory, right? Here, okay. So, which means that CPU doesn't need, for example, if it says, okay, it is reading an instruction from the memory. So it doesn't need for that read operation to complete before it can read the data from the data memory. Why? Because it will use the different set of buses to access the data memory, right? So it means that it is faster as compared to Princeton architecture, right? The one thing which you need to note here is that for data memory, you have a two-way arrow on the data bus. Why? Because CPU can read data from the memory and it can also write data into the data memory. However, for the code memory, you have one-way arrow pointing towards CPU from memory to the CPU. Why? Because code memory contains your instructions and CPU only fetches instructions from the memory. Instructions are not written back into the memory typically. I mean, in like normal or simple cases. Okay. And then definitely address bus and control bus in both cases are from CPU to the data memory or to the code memory because CPU is the active component. So CPU is actually always saying, okay, I want to read data, write data. It is not like that memory chip is requesting or demanding the data from CPU or asking the CPU to provide the data. Okay, so memories are like passive components, and CPU is the active component here. So this architecture is complex, but then it is fast. Complex because now you have more buses to communicate with separately or simultaneously with code memory and the data memory. Any questions? And why we discuss this? Because your ATmega 328P uses Harvard architecture. So it uses basically this architecture. One thing about Harvard and Princeton architecture is that Harvard architecture is typically used in microcontrollers. Why? Because on microcontroller, remember, we have all the components on the single chip. CPU, data memory, code memory, everything is on the single chip. So yes, we have separate buses, but those buses are on the same chip as the CPU and the memory. Uh, we cannot use the Harvard architecture in general purpose CPUs. Why? Because in general purpose CPUs, your memory is too big. You cannot hold it on the, you cannot have it on the same chip as your CPU, and your CPU itself is also very complex, right? So what you do is that in you have separate chip to hold to have CPU and to have memory, right? So these are two different chips, right? So let's say if you have two chips, one is memory code memory, I'm writing it CM, and the other is data memory, right? And one chip is to hold the CPU, or it contains the CPU. So you will have like buses, one set of buses between data memory and CPU, and another set of buses between data memory and code memory. And these buses are crossing the chip boundary. Now, if you remember from our previous discussion, more chip, whenever the communication or the communication lines cross the chip boundary, communication becomes super slow. Okay. So if we use this Harvard architecture in general purpose processors, so our processors will be super slow, right? Uh, because now we will, and it will also become expensive. Now we need more pins here, right? Because these buses are going out of the chip, and our processor will become expensive. Okay, but that's why that in the general purpose processor, people normally use this architecture. So you have CPU, you have two different chips to hold data and memory, but you use the single set of buses to communicate with both. So it keeps the pin count low, right? At least like it reduces the pin count by two. Here, if you needed it six in total, here you need three, right? One thing. And second thing is like we since the communication is slow, we don't want to create more communication bottleneck by creating more buses. Any questions? Okay, we have almost 10 minutes and we can continue. Actually, this is the point where we are supposed to start today. We are running behind to the schedule. So, okay. So we have already looked inside our AVR CPU or ATmega 328-piece CPU, right? In terms of what components we had. We talked about ALU, we talked about PC, we talked about instruction decoder, we talked about registers, but there we were keeping it simple and we were saying like there are like four, we are just representing by four registers A, B, C, and D, right? But actually, in ATmega 328P, you have not four registers, you have much more than that. In this figure, we are showing only 32 registers. Why? There are also more registers other than these 32 registers, but let's not make it super complex. Let add complexity like in an incremental way. Okay. So we have these 32 registers which are named as R0 to R31 and are numbered as R0 to R31, and they are known as general purpose registers. Why general purpose registers? Because they are typically used to hold any data. The data inside them is like any arbitrary data. These registers don't have any special meaning. Like for example, in R2 you can put a value of 10, you can put a value of 100, or you can put a value of 255 and so on, right? So you have these the registers, and together these registers basically make the register file. Okay. And other than that, we have another component here, which we are naming as SREG or status register. Stands for status register. And this status register has 8 bits, and then each bit has a meaning. We will talk about it later, but for now, just keep in mind that we have a status register, we have 32 general purpose register, PC, ALU instruction and instruction decoder. Okay. So in ALU, arithmetic logic unit, so it is responsible to, as I said, to perform the arithmetic and logical operations. Arithmetic, for example, addition, subtraction, multiplication, and logic operations, for example, AND operation, OR operation, exclusive OR operation, NAND operation, NOT operation, and these kind of all the logical operations. Okay. So as I said, we have 32 general purpose registers, R0 to R31. There are also other registers, but we will not talk about them at this point. PC register, we have talked it about earlier. So the job of the PC register is to point to the next instruction in memory, right? Which will be executed, and status register. So let's start learning the assembly language or assembly language uh, of the ATmega 328P by starting a very simple operation, which is basically loading values into general purpose. So we have these registers, right? R0 to R31. Let's say I want to put value, some arbitrary value in one of these registers. So how can I do that? What instruction I will use to do that, right? For that, you will use the instruction load immediate. So LDI is the name of the instruction, right? Uh, and it takes two operands: destination register, the register in which you want to put the data, and the K, the value which you want to put into the value, so into that register. K is like the immediate value. Okay. For example, if you want to put 10, so K will be 10. Okay. So, and this destination register, the restriction of the placed on this instruction is that the registers in which you can put the value or load the value, it can be any register from 16 to 31. Using LDI instruction, you cannot put value into R2 register. You can put register values only in R16 to R31. Okay. So when you execute this instruction, so it is equivalent of saying RD is equal to K. Put K into destination register, and RD can be anything like R16 to R31. So here is an example. So if I say, if your program executes, assembly program executes this instruction, load immediate R1653. So what you are saying is put 53 in R16. So here in this register, you will have the value of 53 placed after the execution of this instruction. And what is the base of this value? 53 decimal. It is a decimal value, right? Here we have another example. Load the value of load immediate R19 132, which basically you are saying put the value of 132 in the register R19. Why only R16 to 31? Okay, that's a interesting question. So the reason basically behind that is that when you here I don't have the opcode for this one. So again, not opcode. When you will look at the binary code of this instruction load immediate, so more bits are reserved for the opcode part, right? So the only bits which are left or which are available to specify a register, the number of those bits is 4. Okay. So, and if you have 4 bits, you can specify only 4 registers. Sorry, only 16 registers at most. One of 16 registers. So to make it more clear what I mean, let me go back. Where was that slide? Yeah, here. So for example, this is like your, let's say your binary code of your instruction. So more bits are reserved to represent the opcode. The bits which are left available to specify the operand are only 4 bits, right? And 2 raised to power 4 is 16, right? So which means that you have 16 different combination of 4-bit binary, right? For example, from 0, 0, 0, 0 to 1, 1, 1, 1, right? So each one of that combination is used to represent one of those registers. For example, you can use this one to represent R16. You can ask why we are not allowed to, why instead of like, if I go forward, you can also have an follow-up questions. Okay, if we have 4 bits and it can specify at most 16 different registers, then why we are using 16 to 31? We can use also, why not possibly 0 to 15? So that is like designer's choice, and I don't have a deeper answer about that. But if you have only 4 bit, you can encode for 16 different registers. Now, it was, I guess, designer decision to use 16 to 31. Maybe there is another reason behind that, which I'm not aware of. I hope I partially answered your question. Okay. Okay, here is another example. Zero remove zero load immediate R23 0x27. So here the number was in decimal form, the number is in decimal form, and here we are saying put the value 0x27 in. So this is hexadecimal, right? So if you want to convert into decimal, you can do that, but the number placed in R23 will be 0x27. The underlying meaning of will be like if you specify 0x27 in decimal form, the content at the end of the day, the binary will be stored. The binary will be same whether you specify your value in hexadecimal form or you specify in decimal form. It will not change, right? Am I clear to everyone? Okay, thank you. Let me do this one more slide and then we can go for quiz. Okay. So let's have a look at arithmetic calculations. So instructions which are used for arithmetic and logic operations, these are add instruction, sub instruction, multiply instruction, and AND instruction. There are also other, but for now we are restricting ourselves to these four instructions, right? So for example, the syntax of the add instruction is this one. You first write the name of the add, you write the like letter, not letter, word add, and then you specify the destination register and the source register. And what the operation is performed, destination register and source register, their values are added together and the result is written back into the destination register. Okay. So here is an example. Add R25 and R9. So what will happen? The content of R25 will be added with the content of R9 and the result will be written back into R25. Why we name this as destination register? Because result is written into this same register. That's why. I mean, it is both. It is a source and it is a destination, but the second one is only a source. This one. Another example, add R17 and R30. So these two registers will be added and the result will be written in R17. Okay, next we have an example, but let's stop here. We can start with we can start the next lecture with the next slide we have now. But I think it's time for the quiz. Let me stop here, and I'm available until the end of the lecture time. Okay, so if you have any questions, you can ask me.